Hello, this is Mike Sayers. I'm a co-founder and the current Chief Technology Officer at Mechanical Simulation. This is a presentation of new features that have been added to CarSim, TruckSim, and BikeSim since our last user conference in 2019. This presentation was prepared for the 2022 user conference, which had to be canceled due to COVID. So this video is kind of the placeholder for the presentation I would have made. A little warning here. Because this is focusing on the new stuff, it's not really appropriate if you're completely unfamiliar with CarSim. If you're not familiar with how it operates, we have some introductory material on the video page of our website. Check with that first. And now for the new features, continue on here. I'll be covering 6 topics here. One is the company, Mechanical Simulation, who we are and what we're about. An overview of the release packages that we have for the different platforms. The architecture, which are features shared by all of our products, and details of the math models, mainly in CarSim and TruckSim, that we've added or improved upon since 2019. We made some major changes in how we provide example data sets, and with a database builder. We'll be looking at that a little bit. And then finally, we'll be seeing how we play well with other simulation tools. So our stuff works in the overall simulation environment. The company. We are a spin-off of the University of Michigan Transportation Research Institute, founded in Ann Arbor in 1996, 26 years ago. We were acquired by Applied Intuition, a software company in Mountain View, California, and this year, and hopefully we'll be around for another 26 years. Looking at the people in the company, we are multidisciplined. We were started by some mechanical engineers with expertise in vehicle dynamics and simulation. We now have more mechanical engineers and software engineers and computer engineers and artists, and also our business and licensing people. Our development teams are for engineering, making models, programming things up, running our operations, demonstrating applications for customers, providing artwork, and providing tech support through our online support center. In 2017, we kind of evolved to a steady release cycle that we do CarSim, TruckSim, and BikeSim twice per year, every December, every June. They're all peer behavior. It's kind of the best that we have at the time of the release. A month before a release date, if something is working, we just test it as much as we can. If it's not working, we postpone it and put it aside for a future release. We have 12 platforms, 2 in Windows, 2 Linux, and 8 real-time systems that I'll look at shortly. They're all major releases. December is when we increment the number to the next year, and June is when it gets the .1, except for Suspension Sim. That's only updated in December's for a yearly release. To do this, we have automated building going around the clock. We have a room with high-performance machines and lots of high-speed disks that are doing everything continuously. We have the monitors showing on the wall on the hall in our office. If it's green, it means everything is good. If it's red, it means something is broken. So anytime a change is made in any source code, everything is recompiled and rebuilt. If a change is made in any data sets, everything is rerun. If a change is made in the documentation, all the PDF files are rebuilt and they're copied into the suitable places for the various products. Once a week at least, and near release once a day, installers are built, so we always have something that's ready to go. And the greenness comes from testing them. If something crashes, that's bad, it makes it red. If the results from the new build are not the same as the previous build, then that has to be dealt with. If there's performance testing, if things have slowed down, we'll go investigate that because we don't want things to go slower, we just want them to go faster. We'll take a quick look at what you get in a release package from one of our products. If it's on Windows, it comes with a Windows native installer. That's an exe file that you launch, and it puts everything you might want for the package in there. You get the user interface, the browser that goes through a database of existing examples that we have. It links to the VS math models to make new runs based on the settings you've made. It shows results of existing runs using VS Visualizer, which shows videos and plots overlaying results from different runs. In addition to the Windows native things, it also has versions of the math models for 8 real-time target platforms that you might be wanting to work with. It has connections for commercial software like Simulink, LabVIEW, functional mockup units, interface, Simian, so that you can run with external software. It has command line wrappers that are programs that you can use from your own software to run our stuff in batch mode for design of experiment, high performance computing, other forms of automation, and some utilities like the scene builder and file converters. To get the data in there, we have a bunch of mini databases, and I'll be showing in a little while how you build custom databases with all the examples that you might possibly want with all these platforms. Along with the installation of everything needed for Windows, we also have builds of the math models for 8 different real-time systems. This is Jinhu, the developer of our RT implementations of the vehicle models. We have 6 companies there, and 2 of them have 2 OSs. So pretty much everything that you need to continue the installation and go on to one of these supported platforms is there in the original Windows installation. The only thing that's not covered in the Windows installation is support for 2 non-real-time Linux versions. We support Ubuntu and Red Hat. We have 2 installers for each platform, one that includes the visualizer and one that does not, in case you need to have something customized for that. Both of them also have a Simulink S function to connect with Simulink on the platform. So you get the math model, Simulink support, and visualizer support. Sometimes you have applications where you need high quality visual rendering with realistic shadows and textures, maybe for a driving simulator or for actual camera sensors to do interventions. We support Unreal. We have a plugin called the CarSim plugin, which will run either CarSim or TruckSim models on either Windows or Linux platform, and we synchronize these releases so that when we have a new product release, a couple of weeks after that, we release the plugin for the current version of Unreal. Some of the advanced users might have a need to tie our math models into a custom simulation environment where you're mixing model features such as your own tire model with our vehicle model or your own aerodynamics and so on. So we provided our libraries for building the math models, plus snippets of code showing how to use our application program interface, API, and some various tools for connecting them up. They're all packaged in a software development kit, which has the libraries, the source code, and lots of documentation. So now we'll look at what's new in the last few years with our products. First, the architecture. These are things involving syntax and file management that aren't specific to any model. We've supported formulas for defining values of parameters and equations being used to set values of variables. We made some big improvements in the friendliness of doing this by having inline operations. So now we can have formulas that have not only arithmetic functions but Boolean operations. And that becomes really important when looking at events. It's also for most of our users are familiar with MATLAB, so we're using exactly the same syntax that MATLAB has. And also our visualizer makes use of these formulas. So if you define a dependent variable made of some output variables for visualizing, you want to see a plot or you want to use them to animate something, that's supported. We added user-defined functions in VS commands. So here's an example of 2 of them in an ADAS example, looking at whether something is straight or curved path. And we have global variables that were defined up there, gain, steer, and L_forward. Those variables are set in a function so that function can be used over and over. In the echo file on the right here, we see that down at the bottom, the function is used in an if statement, and that's another new feature, is an if function that is special. It's a lazy function that only evaluates the arguments if they're needed. It has three arguments. The first is either 0 or not 0. If it is not 0, it evaluates the formula for the second argument, like straight here, and returns that, and it completely ignores the third argument. On the other hand, if the first one is 0, then it evaluates the third argument and completely ignores the second one. This is a real quick way to avoid numerical errors such as dividing by 0. One of the major places for using formulas like this with booleans is in our VS events, and an event is, real quickly, it's monitoring an expression. If the expression is 0, nothing happens each time step. If on a time step the expression is not 0 and there is a specified parse file, a data link here, it will load that and then continue the simulation. If there is not one specified, then it will stop the run. So in this case, we have 3 pending events, and as our simulations have gotten more complicated with ADAS scenarios and others, we might have many collections of events, and we want to maybe reset some but leave the others intact. So that's a case here where we've added a group ID. If these are reset, it will only reset the events that have the type sign detect. Here is another one where the type is not sign detect, it's bike lane. So if those are reset, it will not affect this one here. We are making this available. It's not just a user interface thing. It's in our echo file here. We can see what the events are, and this is kind of documentation for how they were defined at the point that this echo file is written. Also, the log file is extended to show all this information, so when you're trying to diagnose what happened or if something went wrong, you've got all the information available in a fairly straightforward way to understand it. Now, besides VS commands, we have been supporting embedded Python. If your platform supports embedded Python, then we support it too, and that's typically for Windows and Linux. There's one command to load the embedded Python, and then other commands to link them to the internal math model. One of the advantages here is, compared with VS commands, is that you can create and redefine tables. In this example showing when an object is selected, the Python makes a new path that goes around the object, the deer in this case. Sadly, the real-time platforms tend to not have embedded Python, so this is mainly a tool for Windows and non-real-time Linux. A few years ago, we worked to change the architecture of how the VS math models are built. Instead of having custom solver programs for each configuration, we made a library that has all the possible configurations available as modules. This was done first in CarSim and TruckSim using the modules that are shown in the slide up here. We have multiple modules for sprung masses of lead units, semi-trailers, suspensions that can be attached to lead units or semi-trailers. And then in the last 2 years ago, I think, we completed the same modularization for BikeSim. So now there is just a single library for 32-bit, single one for 64-bit in Windows, same thing for BikeSim that has all possible vehicle configurations. The way that these are set up is that when you go to make a run, a command called model layout is encountered. And that is a command that has a string telling you what the modules are, and it lets the solver build up a layout of what the vehicle will be, so it knows how many wheels there will be, how many axles, how many sprung masses, and it can start processing the input parse files to know how many elements there are. All the details aren't there yet, but it does have the basics of where things are attached. The convention we have here is that if there is an underscore, that's used to separate the module names, like II is a CarSim model with independent front, independent rear suspension. Here's one for BikeSim. The front is a variable caster and the rear is a flex frame suspension. In the case of TruckSim and CarSim, where we might have trailers, we use a double underscore to indicate a hitch, something separating a semi-trailer from a lead unit. Also, if we have more than 2 suspensions on a unit, and they're not separated with an underscore, that means that they're tandems or triples in CarSim and TruckSim. And we've started supporting multiple models or multiple vehicles within the same simulation. Here's a TruckSim layout that has two vehicles in it. One is a 2-axle truck with an S_S. The other is a tractor semi-trailer. Now this just gives the layout. Details about the suspension, like whether the wheels are steered or not, and compliances, and is there a powertrain. These are added with additional VS commands, but this is all done after the layout is specified. There's one method that has been available for years to run multiple vehicles in a simulation, that is to run parallel. And in the last couple of years we added a custom screen to do this, to really simplify it. We have the screen down here showing that there are 4 links to run control data sets, each which sets up a vehicle run. The simulation has 4 vehicles all interacting. They use the same ground. They have to have the same pedestrians. So anything that they should share in common does have to be set up in the run control for that vehicle. And then they are all linked to the same Simulink model, which controls the running. The nice thing about this is if you can set up one of the runs by itself to put them into this condition, you don't really have to do anything else. But you do have to make sure that they have the same ground and target objects and so on for compatibility. Now the new method is using the model layout that we just showed on the previous slides, where we can have a single run that happens to have 4 vehicles in it, using the white space to separate them. In this case, we only have one terrain in there because it's just one run. We have one set of moving objects, but we do have to be careful in setting up the controllers so that, say, the yellow car up there has its own path following and speed control that has to be tagged with that particular vehicle, not with one of the other 3. We'll now take a look at some of the features that are new in the math models. We've got 2 categories. One is the powertrain, where we've added motors, hybrid, recharging batteries, all things involved in powering the wheels, and that's in a separate presentation by Dr. Yukio Watanabe. Everything else I'll be trying to touch on. So we have always had initialization of the vehicle model when it starts. The conditions are that you're on a 3D road that may not be level, might have pitch, might have roll. The vehicle components can be asymmetric, the loading can be asymmetric, and you might be moving at a non-zero forward speed. In the past, we had a very simple initialization assuming symmetry, and if it wasn't in equilibrium, you would just let the simulation run for a few seconds to get equilibrium. We've made improvements there to do initial conditions, taking into account the asymmetric loading of the tires and the suspension springs. So we are doing the calculations, and we're also showing some of the results in the echo file, so you can use, and these can help diagnose the behavior and also ensure that what the model is telling you the static conditions are what you thought they were. So we have inertia properties that are a combination of the sprung the unloaded and the payloads. We have the unsprung mass properties of what's steered and what's not steered. We have the static loads from the tires and the springs, and not only the loads but the compression, so those are all calculated independently now and listed in the echo file to ensure that we're getting them right. We've recently made improvements in how suspension properties are characterized in our vehicle math models. First, a little background. What we're looking at on the screen here are 2 suspension sim models, one showing a bounce test and one showing a steer test. We have all the points of the suspension, and we're getting variables that you might measure in a KNC test in the lab. These are also results that not only can be done in suspension sim, but other detailed 3D multi-body software such as Atoms. Now the kinds of measurements that you get on the road are much more limited. You're usually limited to just things like jounce and steer. Well, what do we need to get in our vehicle model? What we really need to do is get the position of the tire relative to the ground. So we have the wheel center and how the wheel is oriented and where it's contacting the ground. That goes into our tire model that comes up with tire forces and moments, which then get transferred through the suspension to the sprung mass. And the way that they're transferred depends on the kinematic relationships between various parts in the suspension and how they move relative to the sprung mass. These are not necessarily things that are easy to measure, and in our math model we don't really care about whether they're measurable or not. We just want to have the right answer. We want to make sure that the way that the forces and moments are generated at the ground are transferred correctly to the sprung mass. So to get these, in the past we would do just kind of an approximation and say, yeah, what we're asking for is close to what you measure. We've now made some improvements. We have a new suspension module that is in CarSim that is called V for a virtual steering axis. And instead of having the jounce at this side and the jounce at the other side, it has jounce and steering rack as independent variables. So those will be used to get the wheel orientation. It's harder to do than to get that data. You have to have a real specialized set of KNC tests, but if you have them, we can make use of it now. There's another improvement that we've made, which is the independent suspension kinematics utility that is a way to let you put in data that you would measure in a KNC test where everything is relative to an absolute ground. They're not the virtual, the relative reference frames that we use in the math model, but it calculates those relative ones based on what you can measure. And there's a keyword that does that. And this is this is showing how it works in a simulated KNC test. And some of the plots are showing just a single line. That means that what's predicted in the KNC is exactly what we put in. Others differ. And this is a case where, say, the sprung mass, or where the longitudinal position of the wheel is taken as measured versus as done with our internal relative frames, and there is a difference of a little under a millimeter in there. So if you need to get your precise measurements into the model, that is now, there's a feature for that. There's a tool to let you take that in. We have a few features involving trailers that were added recently. One is the types of hitches. Traditionally we've had a hitch connecting a lead unit to a trailing unit where they share a single point in common and possibly have torsional springs. We've added that to have some more complicated connection types that have moving trailer parts. They're selected now on the trailer screen. You can say that it has a hinge tow bar or an articulation system. Here is an example showing a hinge tow bar, and the trailer has a hinge here so that the front part, the tow bar, cannot transfer load to the leading unit. It prevents it. It means that in this case the dolly is taking the whole front end load of the trailer. Another type is an articulation system used in articulated buses. In this case we have to have load carried by the hitch because there's only one axle in the back. So the hitch has to support the load. It has to provide pitch and articulation motions, but in the bus configuration they're typically done with this novel design where the pitch axis is hooked to the lead unit and the articulation is hooked to the trailer, and there's like a half a meter or a meter between them. And one of the advantages of doing that is it doesn't take any vertical space, so in a public transportation thing, you can still put baggage over it, or people can walk over it. Another feature of these articulated buses is that they tend to have Powertrain on the rear in the trailer. Now, I said that all the Powertrain stuff is going to be handled in another presentation. There's one exception, and that is that we now allow Powertrains to be attached to a trailer, so that instead of getting a pull situation, we have a push situation. We set it up by setting the Powertrain unit to be the unit of the trailer, and it's just any kind of a Powertrain type. If it's a one-axle trailer, then it has to be a rear-wheel drive. And when we look at the echo file for the simulation, it's showing the information in there. What's the Powertrain unit? It's installed and it's of type rear-wheel drive. And so the drive is on the rear axle, the only axle of the trailer in this case. Next, I'd like to show some changes that we've made in our built-in driver models. The first one is path following. We made a major improvement a few years ago to allow a simple controller that is based on having a preview point and a reference point, and we steer just by having the angle going from the reference point to the predicted point along the path. It's used in race car situations where we have limited limit slip behavior, and it's used in this Australian test called a PBS, performance-based safety test, or performance-based standard, where the driver is supposed to be able to use a mirror to monitor the location of the outside of the right front tire and make it follow that dashed yellow line. This works well for that kind of thing. We put the reference point on the tire. We have the preview point a little bit in front. If we need to get better behavior, we can use VS commands to add integral control, as was done in this case. Other changes to the model are that we have the option for torque control, and the coordinates of the point being brought in can be generated externally from Simulink or VS commands, anything to bring the coordinates in. This also works if the vehicle is going backwards. In that case, the reference point is near the rear axle and the preview point is behind the vehicle. Now, once we start doing that, we also want to think, can we do this with a semi-trailer? If we have a trailer on here, like in this case, can we steer the lead unit, the motor vehicle, so that the green dot there follows the path? Now this is a little different because instead of having a steer angle control it, the trailer is being controlled by the articulation angle of the hitch. So we have made a trailer backing control that is added to this. It's actually very easy to use once we worked out the details. There are just two things to do. One is use the command to put the TBC in place, and the second is that there's a parameter that you can use to tune the behavior. Details for this are covered in a new tech memo that was added this June to describe the behavior. Our built-in driver controls also include speed. We've had speed control for a long time, and it's mainly used to generate acceleration requests, and then the acceleration request is used by the powertrain to generate throttle, or by the brake system to generate brake control to change the speed to go up and down. We also have an option where it might use a preview. Using the preview mode, it looks ahead and says what's the speed limit going to be in the future, and what kind of acceleration limits can I tolerate for lateral and longitudinal directions. So if it means braking in the future, it'll determine what the longitudinal acceleration allowed will be and determine how much braking to apply. Or if it's going to be a higher limit, how much can it accelerate up. And these acceleration limits were first put in place for limit performance, as you're seeing in the video here, on a local racetrack. But there are many other applications where we're now using this as the main way to control ADAS scenarios where we need to stop in a specific position. So let's take a look at how that works. This is the path preview control where we put in limits for acceleration. We put in an ID telling us what a speed limit would be, or a transient. Now this is a special kind of function. We're saying that the target speed is going to be 3.6 kilometers per hour until we get to position 0, a station of 0. What we're going to do with VS commands is rescale this, because 3.6 kilometers per hour is 1 meter per second, and we take that 1 meter per second and say scale it by the current speed of the vehicle, and that would tell it to go at your current speed until you get to this position 0, and then you should be going at 0. So here is the simulation, and you see that the speed is going down. It's using that longitudinal deceleration to make the vehicle stop right at the stop sign, and then it can continue on with the ADAS run. It'll go into an open loop throttle for a little bit, and then it'll go back to the speed controller to look at a target speed that is ramping up based on our acceleration limit. And there's one more built-in closed-loop control in our speed behavior, which is for manual transmissions, doing the shift control. If you have a mechanical clutch, then we synchronize a clutch control and a throttle control and the gear shift timing to give a closed-loop controller that kind of mimics what a driver might do or what an automatic mechanical clutch transmission would do. We set that by linking to a clutch timeline set of three sets of parameter for the clutch, throttle, and shifting. And then you see in here, as we come down to the stop, it's braking to a stop. The clutch is engaged at the bottom or disengaged to prevent stalling the engine. And then when it accelerates, it does clean shifting to go up. It's pretty minor behavior trying to get realistic things, but it's actually kind of complicated to have all these signals interact and not cause numerical problems with our simulations. Now when we get to the ADAS simulations, we have typically an ego vehicle and multiple moving objects, where the moving objects are programmed to behave as pedestrians or bicycles or other traffic vehicles. In this case, there's one ego vehicle. That's the blue car that is coming from the other way that has the yellow force arrows on it. Everything else is a moving object, and they're operating under acceleration control to give them realistic motions. Acceleration control is basically F equals ma. We're saying that the acceleration is the command, and they move based on that. They have brake lights that are triggered. They are shown to be on if there's deceleration that would normally be provided by a brake system. They also have backup lights if they go in reverse, but you don't see that in this simulation. Besides having the longitudinal acceleration for their speed control, they have off-tracking when they corner so that the rear wheels follow the front wheels and you don't see that silly pivot that looks like a slot car in some simulations. We've added more controls for how the shapes are attached to the moving objects to give more realistic detections. Here's a case where we have irregular polygons for the building shape and for the bus over there. We can see that the detection of the pedestrian depends on where we are in the simulation. The building does not have a corner there. It's got 5 walls, and we'll see how that's put in here. We go to the moving object screen and say that it is a polygon. Its coordinates are x and y. This is what the shape looks like, and it's just a set of xy coordinates, so that right now we don't see anything. The male pedestrian is blocked. Now he's visible because the building is not blocking the view. Now this is the extending this further. Instead of having a moving object that is programmed based on VS commands, we can attach the moving objects to vehicles. In this case, we have a TruckSim simulation with 2 vehicles in it, and there are 3 moving objects attached to the 3 sprung masses of the 2 trucks. Here's the tractor semi-trailer. We'll go up and see that we have a I unit. This is a feature in the moving object screen for customs. It says attach this to the current sprung mass unit. That was the lead unit. We're using exactly the same data set, attaching it to the trailer. The scaling comes from the trailer sprung mass, but the detection comes from it being a moving object. Besides having multiple vehicles in here, we also can attach a moving object to a sprung mass to get details for a collision, such as a Euro NCAP simulation where we have a dummy pedestrian dummy crossing. We need to know exactly where the contact occurs, and we do that because the vehicle sprung mass has a moving object attached to it. We'll take a look at that. It's the same thing. We attach it to the current sprung mass, and lo and behold, the shape of that polygon matches the shape of the vehicle in here, so that we know not only that there is contact between the pedestrian and the vehicle, but exactly where it occurs based on that shape. Now we also have a sensor in the vehicle to determine where the pedestrian is, and it uses that to do the emergency intervention to try to avoid the collision. We have added more Euro NCAP examples. This is one where It is called a cutout. Our car is following a moving object that looks like a vehicle, and the moving object gets out of the way and reveals a stationary object which we would like to not crash into. That's the purpose of the test. So in support of these Euro NCAP things, we not only have some examples, but we have custom animation shapes for the fake vehicles and fake pedestrians and even bicycles. And now I'd like to present one of the most significant features that we've added that gives you access to more example data sets for all kinds of exotic combinations. It used to be that when you ran the installer from Windows, you would get two folders installed. One would be all the programs that would be in a read-only location, and that's what you still have. And the other would be an example database that is what we provided that had a little bit of everything. So that would have all the stuff that you needed that didn't need a special license. To get the RT stuff, you would go through a separate step to import example data sets using a CPAR. When you did the installation, this is an example of what it looked like in 21.0. Starting with 21.1, a year ago, we got rid of that. We take every data set that we use for internal testing and we put those in CPAR archives that are installed forever in your installation that you can use or not use as you see fit. The first time you launch the product, you get a screen here saying that there's no database yet. Would you like to make one? And you have several options. One is that you can show your old data sets and go from there, but the main one is that you'll use the button down there that says Open Database Builder. And that brings up a new tool that gives you 6 options that are in here. A minimal one just has a few basic runs, the quick start guide, and all of the new examples that have a star category on them to show new features. Another one is for basic ADAS or basic vehicle dynamics. Standard ADAS and standard vehicle dynamics have a lot more runs in those categories. And full is all the stuff that doesn't need an extra license. That's similar to what we used to have. But there's also this option to show all the CPAR archives, and when that is checked, you see everything that we have in there. That includes all the RT stuff, the driving simulator ones. So for example, in this setup, we have the standard ADAS selected and a DS desktop. When we run that and look at the database, these are the kinds of runs we have. We have all the basic ones for ADAS in here, and we have a bunch of runs using the Logitech controls for a driving simulator. The idea here is that you're going to make lots of databases. You're going to manage many of them. So everything we've got, we put in a read-only archive that you can keep installing them over and over as you see fit. If you trash something that we've installed, no problem, just install it again or do a different combination. There are no limits for how many of the CPARs that you might use, so we'll be expect us to include more in future versions. There are no built-in numbers, no built-in limits to the number of databases that you can have. This is the number of databases that I had in 22.0 when I was making this presentation. I didn't use 22.1 because I had wiped everything out for that. So whenever you boot the browser, you've got instant access to everything you've done recently. Once you're in the browser, if you want to switch to another one, you go to the File menu and go down, and these are databases that you've used recently. So we're trying to make it easier to manage multiple databases, and also to make sure that if, say, you're going to evaluate a DSpace version and you want to install it, you've got all the examples right there ready to go in your basic installation. Now, the last thing I want to talk about are working with other tools. And there's not that much that we've added because we have pretty good support to begin with. These are the tools that we have with installed support. You don't need to do anything extra for Simulink or LabVIEW or Simian, ETAS, ASCET for the real-time systems. You've seen that all the parts are in there. For functional mock-up interface and FMUs, we support 16 possible ways of doing it. And we have support for popular third-party tire models. Also the plugins for Epic Unreal. So those are already there, but we did make a few improvements. When it comes to how we model the ground underneath the tires that the vehicle is driving on, We have two options. For over 20 years, we've had one option, which is using VS paths and VS roads to define a 3D surface. And that's great if you're making something from scratch. But if you're trying to bring something in from other software, we need another format that is more universal. So we have something called VS Terrain that is a cluster of points that can be provided by a variety of tools. We mainly use it to import FBX 3D data files and also OpenDrive files. These are XYZ coordinates, and for each XY point, there's a corresponding Z and also a friction and also a tire rolling resistance coefficient. So the main reason that these exist are to support Unreal and other sources of data. So when you're making your run, you really have two options. You're either using VS Roads or VS Terrain. And when you're using VS Terrain, we don't have a native builder, but we do have Scene Builder, which lets you build tiles, making use of existing VS Terrain files. And we have VS Terrain Utility that lets you import data from other formats and make use of them in our software. Another add-on that we have, we've had it for several years, and we keep making improvements and revisions to it, is what happens if you want to run with Unreal and Simulink. Simulink wants to be the master. You have to run under Simulink if you're going to work with that. At the same time, Epic Unreal wants to be the master. If you're going to run under Unreal, you have to run under that. Unreal will not run under Simulink, and Simulink will not run under Unreal. So the solution is that you run both of them at the same time. They do co-simulation. You hook up CarSim or TruckSim with the one that needs the fastest communication, and then you run VS Connect to synchronize them so that they remain that they don't go rogue and go independent. Here's an example of how it's being done with Unreal. This is just our proving ground in Unreal, and then we'll go to an example where we have two vehicles that are connected. The second one has a cruise control implemented in Simulink. So here are the two vehicles. The one in front is full vehicle model running with the built-in driver model, and the one behind is running with Simulink doing the adaptive cruise control. So we have two vehicles in CarSim plus Simulink plus Unreal. Well, if it weren't for COVID, I would be taking questions and answers right now, but I guess this is just the end of the video. We have other videos on our website, and happy to take any questions via email. Thank you.